inviting me and to introduce part of my work. And I must say that I'm in depth with the previous speaker and the question that have been raised now, because all I want to, say today, and my main message of today is that it must be followed the two sides of the introduction, where metrology is looking for challenges from new frontier, and the other side is biology is not so simple to take it. Okay, so there is a clear difficulty. Any biological tissue and matrix has a very intrinsic high level of variability. So the challenge is to find out a robust analysis that can nail down some of the variables, to maintain them in a strict interval and make them reliable. But also, you must be concerned about this in terms of what you are releasing out in society. Because if you have a very variable background and a lot of variable inside it, you have difficulty to make measurement, and when you do measurement, you must establish if they are applicable in real society. And what I will do today, I will try to address this question of mine while dealing with the project that we are working on that is called Fit Code. We basically apply a new method that we have developed to the identification of different ingredients that are present in feed samples. Okay? So you basically, I'm keeping on going on because there's a problem with the presentation. So when you have a feed sample, you have a different plant species inside, okay, which are present in different forms. This is a challenge because any feed sample may be different from another. So basically, you must cope with the fact that the intrinsic biological variability that you find in a feed sample is stressed at its utmost. And at the same time, each plant species that is inside may be present in different form, and therefore contributing in a different way, or either the metabolite that you're going to measure, or in this case, the DNA. So you must be concerned about that, and work out a method of measurement and standards and protocol that are more suitable for this kind of analysis. Now I have to stop because I need a presentation to go on. Yes, is this one? This one. All right, that's fine. Okay. I try to do my best to entertain you.
Thank you.
All right. Okay, can I use the arrow because I have much more better. Can you see the arrow? Yeah, I think so. Because otherwise. All right, I've already introduced the topics on which I'm working. The project is the Fit Code project, and there are three reasons why I'm talking about this. One, I've already anticipated, because here you work with the biological matrices that are rather complex, because they're made by different ingredients, and that they can be present in different forms. The other thing is, nevertheless, this is a project that has been sponsored by the European community. It's in its middle of action, and they ask for validating the method by which we try to, with molecular genetics method, we try to reveal and to measure the composition of the feed sample and see also the quantity of contribution of each one of the ingredients. As anticipated, you also have some kind of, social attention, because of course whatever you do or whatever you will standardize will have a consequence in the real world of feed trade and commerce. This is exactly what I'm saying. There is a social attention on that because, see, on the one way, the European community has released a lot since 10 years from now, a lot of regulation concerning feed, sampling, composition, hygiene standards, certification, and is still going to release some more of that. And at the same time, you have the stakeholders that are growing their awareness about this because they want to be able, they can be two types of stakeholders, the feed producer, and therefore they will be interested to understand, to use something to certify their product, okay? Or there are the end users that may be very variable people that can produce meat, they can produce milk and cheese and so on and so forth. And they ask for exact percentage composition of the feed sample they buy, the presence of absence of some species, the origin of some species or variety of those species. And of course they ask for identification of possible frauds and contamination rather than compliance with the production of product of origin from a specific region, okay? Because many of the shipping or production forbid the presence, they forbid the presence of specific plant species. So, as I anticipated, all these require, attention, because at the same time you have to deal with something very variable, but you must be rigorous because you have to propose measurement, but at the same time you must be careful because it's going out in society. The method that I, of course, have to explain to you, because otherwise I could not explain all the story, is a method that we have developed. It provides a code for each plant species, okay, with the same reaction, but putting it into the reaction tube a DNA that is coming from any different plant species or from a feed sample. You will produce from many different plant species a specific DNA code, because you amplify selectively a region of DNA that is present in multiple copies, but they are different in length and sequence from one species to the other and within the member of each plant species. So each plant species has its own DNA code that is different from any other of the other plant species. And at the same time, each band that you amplify is a source of DNA sequence that you can use to design probe to amplify, more specifically again, that particular target region of that plant species and work out a quantitative measurement. You see, this is a simple example in which you see 4 different plant species with that DNA code, soybean, barley, maize, and wheat, and you see them present in a feed sample where they are both all the 4 are present, and you can recognize them from their specific peak that is being colored with a triangle. You see how you can prepare the probe. So you can isolate one of the bands, as I said, and then challenge it, the amplification, designing new primers, and that they will anneal just with your favorite plant species and not with the genome DNA of any other plant species. So you find selectivity here. And now, with this primer, you have a probe that you can use in quantitative assay. Before getting into it, let me just show what is the feed code platform and feed code probe. The feed code platform is on top, is a series of operations that eventually will lead to the production of profile that contain all the peaks of all the plant species that are present in that feed sample. There's a software that we have developed, the feed code software, that will recognize the contribution of any different plant species. At the same time, starting with the same DNA that you have extracted from your feed sample, you go for quantification. Quantification is now done with real-time PCR. That is a method, a comparative method that requires the calibration curve. I'm not talking about digital PCR because I don't have time. Quantitative PCR is real-time PCR is drawn, as I said, is designed over the information that we can have amplifying and isolating all of the first intern sequence from any of the plant species that we want. 30 in this case because 30 were the plant species of interest for the project. So we have a ton, a lot of sequence information on which to design our primer for quantification. The reaction that we use to be selective is called a real-time Tachman assay, because we designed 2 primers to amplify the specific target sequence into the genome of your favorite plant species, and also internal fragment that will add selectivity. So 3 selective primers. But these internal primers carry a fluorescent dye that is quenched by close proximity of the quencher. But when the amplification reaction starts, the internal oligo becomes displaced, and the distance between the quencher and the reporter may be released fluorescence. And fluorescence is released faster if you have if you have more target sequence. The kinetics is faster than you have less target sequence. And so when you validate this procedure, you must find a condition for your probe that is specific for your favorite plant species. You set up the annealing temperature so that it will react, your primary will anneal just with your plant species and not with all the other plant species. And then you must, define the criteria. Sensitivity criteria, you must define your limit of detection, which is the minimum amount of target sequence that you can confidently find at least in 95% of your detection, establishing a cutoff level, that is, that you consider anything that come out before 36 cycles of quantitative PCR. That means that you have amplified your DNA at least before 36 cycles of PCR, but that means that you pass a certain specific threshold. You also care about specificity because there must be a difference in the reaction and kinetic between your specific plants and all the other ones. That we have accounted for 3 log, which means across reactivity less than 0.1%. And then, of course, you will look also for transferability, because it doesn't make any sense that you make a probe specific for peanuts or for rice and cannot recognize equally well all the varieties that belong to that plant species. Here you have an example of what we do with a real-time PCR. This is the probe that we are preparing specific for arachis, which is peanut. Here is the reaction I was talking about. They have been obtained, this is the kinetic of reaction, this is the cycle. This means that at this amount, a 24 cycle, you start to cross the threshold in presence of this abundance of target DNA. This abundance of target DNA amount for 10 to the 4 genome equivalent, diploid genome equivalent of peanuts. We know what that means because each plant species is a C value. The C value is the value in weight in picogram of any employed genome of any plant species. You do a serial dilution and you see you cross the threshold, at the following cycle, and you make a standard curve. Now you have a tool in which you can define in your feed sample how much of the plant species is present, comparing and interpolating with the standard curve. And you also must define and can define what is the log. In this case, the log, since we have made a cutoff at 36 cycle, is 3 target genome copy for this kind of assay. Now, going into real world, because as I said, we must be careful because all we do is has to, it may have an impact in society. What you see here are 7 different, a little bit hard to do this, 7 different feed samples that we have obtained from Consorzio Parmigiano-Reggiano, who is a partner of us in this project. You see, first of all, as you see, you have different ingredients in terms of plant species, but also different form. Okay, you have molasses, you have flour, you have flakes, you have hulls, and so on and so forth. This is the analysis that came out from the platform. It's pretty informative because I already tell you in green line what is indeed there, that is in compliance with what was declared. In the yellow, in the orange, you find out that the platform cyst is not very sensitive at a very low level. It tells you what you are looking for if you want to confirm that some species are present. For instance, sunflower and sugar. And then, already you know that you read the character that there are plant species that are present but not declared. And in one case, flax, there is a species that was declared and that is not present. Rice is important because in these are feed samples that should be used to prepare Parmesan cheese. And the distributor production of Parmesan cheese forbid rice as a present. So you have already set an alarm for rice presence in this feed sample. Okay? I cannot go. Why can't I go? What's the problem? Oh, okay. This is just to say that flax is not there. I have no time to enter it. Just take rice. For rice, we did the same thing for peanuts. We set up a standard calibration curve and make sure that it's the same for all the different variety of rice. So it's safe that we can detect rice, okay, no matter what variety it is. This is the standard curve, but the limit of detection for rice is 10 genome equivalent. When you go and answer the feed sample, what you see is that in the feed X42, you ran the feed sample DNA with your probe for rice at the same time that you do the internal standard curve. You find out that you have a 1200 genome equivalent of rice present in feed X42 that account for 1.5% of the total DNA
that you have used in your reaction that is also rising in this other feed XA. And here comes metrology in some way, because what we're providing here is not only that rice is present that should be forbidden, but now we are saying that rice is present to a certain amount. But that amount is DNA over total DNA. It's not the amount that we've been asked from the stakeholder and all the people. They were asking about, they want to know how much rice is present in the starting material. And as far as I know, this kind of, connection is not so easy. It's not even done at the level of detection when you do that for looking transgenic into feed cell. Okay, you always provide data on DNA over DNA. It should be no problem, because after all, if you have why does it work? Cannot go on. Oh, if you have I must push very hard. Okay, so it shouldn't be that a problem theoretically, because once you establish what is your genome equivalent of your target sequence of your plant species, and you consider the dilution factor of the volume of X at the beginning, you multiply for the C value, that is the weight in picograms of that plant species, and you got the weight of your genome targets of your DNA for that species that you have measured. If you divide that by the DNA recovery, that means how much DNA total you can extract from that particular amount of feed sample, theoretically you should find out how much in the starting material you have of your species. But this is true only if the DNA extraction protocol work routinely is the same and provide you the same data routinely, regardless from the type of feed material you're starting. DNA should be equally represented in the DNA extraction. They come from different plant species. They may be extracted with a different efficiency. DNA should be equally amplificable. DNA should be equally sensitive to the inhibitors. So these are all challenges, and that's the reason that I'm finishing this talk, if I can go on. Okay. By highlighting to you all the different challenges and source of biological errors that you may find. I'm doing this not because I'm scared about it and I think it's impossible. I'm doing this actually, I'm excited because in some way there is a way to solve this problem, okay? I've learned something also of the introductory lecture today. But see, you have a lot of source of error here, starting from sampling. So the feed sample come in big bags, and you work with very little amount of the sample. So you have to produce meal that is very representative. You must be careful about the different composition of plant species. When I said that there are different in forms, it means that not only the same forms contain the same DNA. Flakes, for instance, contain very poor DNA. If you have corn flakes or you have corn seed, you are likely to do some error because corn seed contribute with DNA a lot, but corn flakes no. And then you have, this is a problem, you need a reference material, okay? Because theoretically you should have a reference material for each different feed sample. Okay, on which you can spiking your ingredients that you want to check, and so with increasing amount, and then you can do a really good standard curve. Then you have a problem also in DNA extraction, because sometimes you must be aware of the fact that the variety are different in genome size, although they belong to the same species. They have to cope with a copy number, with the ploidy that it may be different application. And then you must be aware of the fact that your extraction method can be really representative, but do not make a favor, it really is working well for any plant species that is there. For instance, DNA from grasses is a little bit more easy to extract than from oil plants. If they are combined all together, you may have errors there. Also, you must be careful about the presence of inhibitors. You must know if inhibitors are there, and your kit for amplification is not sensitive to some of these inhibitors, or even worse, it amplifies worse some target DNA than others. Then when you go on a probe, you must be careful about specificity and which kind of reference sequence you want. I told you that we use as a reference the genome and the target genome of each isolated plant species. Genomic DNA, that is the target sequence, our primates go there. But is that correct? Maybe you want to isolate the target sequence, clone it, make a recombinant DNA, use that. Okay, this is another possibility. Then you have to define the limit of detection, and you have to establish a way, a measurement to rescue the amount of, as I said, in terms of, starting from DNA amount in percentage over total DNA to real amount of the plant species in the feed sample, starting feed sample material. So you see there is a lot of work to do, okay, and what I want to say is that in our hands right now, just to give you some numbers, we have analyzed now hundreds of feed samples, and here there is what I meant before with social acceptance. Out of, let's say, 100 feed sample, our experience is that 50 of them are not in compliance with the labeling, okay? That means that very often, not the discrepancy is related to an important amount or plant species, because very often, for instance, we find contamination with soft wheat that is normal, that is present wherever feed is handled. But you have to also consider that sometimes contamination is a problem, because I showed you, rye shouldn't be there. So you have to set up a way to say, okay, maybe a limited cutoff or whatever, and say, no, this is prohibited. But at the same time also you must understand that what is the real social impact and relevance to find out that your feed sample you have 1 or 2% of soybean. Is that relevant? See, these are numbers that can fluctuate very well, because if you just make an error in DNA recovery, okay, you change and you just start 50 with less than 50% efficiency in DNA recovery, you already, change the value to 1 or 2%. So, I mean, somebody has got to, this is the work that has to be done. And we must make reference, we have to solve the problem of the standard, the reference material. We cannot simply make a reference material for any feed sample that is in the market. Feed producers could do that though. And all the other issues that I've put your attention. Thank you very much.